We're going to be working on the second half of Chapter 2 this evening, and I'm going to be going through the PowerPoint. Topics for this chapter are listed on the next two slides that you can read on your own. And the topics in the second half are kind of interesting, and this is where we start to kind of ramp it up to the point where now we're going to start looking at multiple tables at the same time. That's kind of a big thing, and how we can do, they call it multiple table queries, but like linking tables, linking columns, sometimes within the same table, sometimes from other tables, and this is really where I think databases start to kind of take off in their structure. Once again, we're going to be working with the Cape Cod databases as our example. And they just have a little background here. It says they got 15 retail stores in the US and Canada, an internet store, and a mail order department, which is typical for large retailers, I guess. And then all the stuff is recorded in an Oracle database, of course. Brought to you by Oracle. So they give a little diagram here. Now, I'm not going to sit here and granularly look through this, but if you were ever doing a DBA work and you were building a database from scratch, for example, or you stepped into a production environment where it's already up and running, information like this can be invaluable, because if you, as a database person, understand functionally how the business operates, their operating procedures, right? Their information flow, if you'll have it that way. Then it makes a lot more sense what you're doing in the database. So if we, this is a business that's selling retail goods, but let's say we compare it to an educational environment like here, it helps to understand that students have to register for classes and get grades and pay a bill and get transcripts and things like that, maybe graduate. And understanding those procedures helps you with your database work tremendously. And sometimes it's, I think, pretty critical. Now, when you start to take all these different sources of data, right? So all the different stores have point of sale systems, and and people don't think about this. You walk into a store, you grab a product, it's got a barcode on it, you run it over a scanner, and it gets popped into the machine. It pulls it up from the database, gets the price, subtracts it from inventory, writes a report, and it all stores in the database. And that's very, very common. In terms of what kind of database system that is, we typically would call that a transaction processing system. It actually has a formal name. But neither here nor there, the information gets stored in the database and then gets moved into other environments. What's kind of interesting is, because they have a bunch of different databases probably within this organization, not unusual at all, but it is possible to kind of link those all together into what we call a data warehouse. So you have different databases, and it might blow your mind a little bit. We're going to learn how to join tables together, but you can also join information from various databases together. And if you think about if each store is got their own database doing the same thing and they link them together, well, if they're the same thing, are kind of not a big deal. But if you have functionally different systems, so for example, they're saying if you're getting information from sales, you're getting information from who knows what, maybe a vendor database, or who knows, all that combined ends up forming what we call a data warehouse. So kind of an interesting thing. Okay, they talk about how things work, and anything, when they say operational database, it's anything related to the operations of a business, right? And that can be many different things. Sales is a big one, inventory is a big one, because those are the things that the business does, right? Rather than necessarily, maybe you might have an employee database. Well, it's not that that's not important, but it's not the operation of the business. Does that make sense? All right. One of the things that they're showing here is how the order or the sales database things all tie together, and you can study this if you want. But if somebody orders something, It's broken down into all these various tables, so we're going to be doing queries across all those. They break all the tables down by data type and structure. Nice little list like that. And then they also show us the connections between the tables in a more like visual database kind of way. And maybe that makes a little more sense to you. But I want you to notice as we're working on a slide like this and you start to like dig into what the contents are, that what's happening here is you get an order number, and then that order number, same order number, is also in a different table because when you place an order, you might order one item, right? But you might order multiple items. And so one whole order might be listed in one table, but each individual item is also listed in a separate table. Why would you do that? Why would you be so granular? No answers?
Basically, so you don't have to redo the same information over and over again.
Right. That's really what it comes down to. Now, we're not learning about normalization yet. But if I walked into like Burger King and I bought a Impossible Burger or whatever, or a Whopper and fries and a soda, and I got everything, same thing for all my family, right? And they're all like listed in the database because they are, right? You're doing it at a register. And you walk up and you say, you know what, my Impossible Burger is pretty darn impossible and I want to return it for a regular one, right? You don't want to have to redo the order as well because it is broken down into a granular piece, so maybe you refund that one item. It doesn't mean the other stuff is canceled out. But if you're putting in the information over and over again, it makes a lot more sense to store it separately as well. Then you go, when you go from these individual items, the SKUs then attached to a SKU table. And that's like when you scan something, how do they know how to pull the price up, right? Because it's in the table, It pulls up the barcode. A SKU doesn't necessarily match the barcode. That's an internal product number for most companies, and then it just looks up a price, and that's how it goes to the register. It's not like a feat of magic. So usually those things are pulled up from databases. Some cash registers do it themselves. Then in terms of, you can also list the buyer, and then that buyer can also tie to a different table. So that approach, I think, is really important to understand as we move forward. Just another example there. All right, so we know this stuff. This is just, I don't know why they have to repeat it every single time, but here we go. So now we're going to actually start querying two or more tables with SQL, and this is where I think it gets fun. So once again, we're going to be working with Cape Cod, and I'm going to be selectively taking some of these queries and dropping them in. So before I begin working, I'm going to bring up a new query. And since I want to work with Cape Cod, what should I type first? Use, that's correct. So use Cape Cod. Let the auto type work for you. And that, I'll tell you what, that's kind of a hard one to let go of. If you're used to typing everything manually, and yeah, I think you shouldn't be. I was watching some people work, and they were using a higher end tool, and they insisted on typing everything out. I'm like, why are you doing that? Well, because I want to make sure it's right. But it's pointing it out to you. Why not just arrow down, because that's all you have to do. I don't know if you guys caught that or not, but as you're typing, just arrow down until it highlights, press enter, and it's there. And of course, the reason we do the use statement again is to make sure that all of our subsequent statements are now attaching to this database. People that get really paranoid will put this on every SQL statement. You don't have to do that as long as you don't hop around between different databases. All right, so now you can. Yeah, you can. You can also use your mouse. That works too. You can just like use your mouse, click, double click, whatever. All right, so let's go, let's pull up that first command now. All right, so it says we want to know the revenue for water sports items which have with SKU values. All right, so we're looking for particular items. And in this case, they're doing ones where we're using the in statement, so we're looking for all these different SKUs. And notice they also have, we want to know the revenue for water sports items, which have these particular SKUs. So those SKUs are all in the table here. I guess I'm a little perplexed as to why they have some extra ones. Is anybody thinking the same thing? Because it seems to go a little beyond that. Why do you think that is? In other words, I guess what I'm asking is, does this where statement match what we see up here? It does not, actually. Really, it's this value is important, that one's important, this one, and this one. Correct? Or am I not seeing it correctly? And how are they figuring out the revenue? They're taking the extended price and they're outputting it as a separate column. So it's going to create a total for us. Now, when I paste this over, I'm going to get rid of those extra values. And I'm just going to get rid of this statement here. And let's see, if I remember right, none of these were in there, correct? These are really the ones they're asking about. I'm trying to be intelligent about it, folks. Maybe it's working, maybe it's not. All right. Now, interestingly, you notice I'm coming up with the same answer. Makes me wonder if it's like a trick, but it's not a trick, but yeah, so what they are saying one thing here and doing another down here. So be mindful of stuff like that. Okay. Is this all coming from, is this coming from multiple tables? No, it's coming from one table. All right, let's go to the next step and just start seeing the clarity here. Now, let's go ahead and pull in the SKU data where we just pull in water sports, and then you're going to see all the SKUs that come with it. And then think back to the previous slide and see if that matches up. I'm going to actually do a new query on this one. It just makes a new tab. And there's a little strategy here to me doing that. All right, so you got all the different SKUs. So a couple of them were there and a couple of them weren't, but we did pull those all in. Now I want you to take a look at this combination approach. And now sometimes people will call these, subqueries, if you want to think of it that way. And notice the approach here. So we have a standard select from where. So, but the in statement, so like the stuff that we're filtering for, automatically is selecting all those SKUs. So conceptually, that part of it is generating the numbers that we see here. So rather than go find the numbers and then type them in, right? Well, why can't I find the numbers and just directly inject them? And that's really what's happening here. So we're basically putting in the same numbers and we should get the same output. So if I run that, proof of concept here, I'm not sure that it'll exactly match up. Doing another new query, why not? And let's run it. And it still comes up with the same thing. It does tell us, though, that those ones that we did, the original ones, those are the only ones that have sales, apparently. Right? All the other ones in between were actually irrelevant. Okay? So we can pull those numbers in by doing a separate query and then using the results of the query to run another query. Kind of interesting, right? I'm always a little, hesitant to just kind of brute force do that unless I know my database really well. Clearly, this author does. So, all right. So some people will call these a nested query, and then some people will call them a query within a query. Whatever you call them, it's pretty important that you're understanding what kind of output you're pulling in before you just go willy-nilly running it. And it says here, note that all SQL queries using subqueries are still effectively single table queries in the sense that only columns of the top level query can be displayed in the query results. So the one that was inside the parentheses, we're not really seeing the result of it, and that can be a little uncomfortable, frankly. All right, so let's move on to the next one. Now this is where we're kind of going into the rabbit hole a little bit, right? So we're going to run a query that's going to feed a query that's going to feed a query. And yes, that is completely allowable. So we're going to be going multiple layers deep here. So the first part of it, well, it's not exactly the same because we were pulling in from order items before. But here we're going to find distinct buyers, right? So there's not going to be duplicate entries of buyers, right? From the SKU data table, and then we're going to select from where the SKU order item is in, you know, the order number for the month of January in 2018. Now, let me just talk through this a little bit. I probably wouldn't write a query like this because I think it gets a little watered down. But it's interesting that you can do it. Where you might find yourself doing this more often is if you already have queries built that do this, if that makes sense. And then either you're copying and pasting it in or you're structurally doing something else. So let's try running this one and see if it works. But it's remember, the topmost level of this, that's going to be the one that actually counts. So there's the code. We got a query inside a query inside a query. And what's wrong with this one? You guys see it? Yeah, the smart quote. Thank you, IntelliSense, for finding it for us. Next step here says querying multiple tables with SQL joins. And joins are really important. I mean, I don't know if you've experienced these before, some of you that have done this. But there's basically a couple different ways to do this and a couple different types. First, they talk about what we call the explicit join. So the point of this is to combine multiple tables, remember? And it says the explicit join is used as part of the SQL statement. The implicit, and this is kind of a hard one, I think, initially to latch onto, is not used as part of the SQL statement, but yet it still does a join. So what does it mean to be explicit and implicit? What's the difference between those two words? Because therein lies the answer. Yeah, and that's a good way to think of it, Brenda. Implicit means it implies that we're doing it, but we're not saying it. Explicit means you're saying it. And sometimes, you know, when I have a difficulty communicating with people, you know, it's like, you know, are you going to the movie or not? Yes or no? Well, I'm going to go out to dinner and then I'm going to get some gas. That's not, you're not implying anything there. You know, so sometimes I always tell people to be explicit with their answers. So I think that's a good way to remember it.
So that's explicit defines the exact what it's going to do what?
Yeah, well, explicit means that we're actually saying join in the statement. That's really what it means, Vaughn. But it doesn't mean that you can't join tables together if you exclude join. You still can. I'm always a little careful and pensive from it. So let's take a look at the first little example here. So they're calling this one a cross join. It says combines rows, or combines each row in one table with every row in another table. That's kind of hard conceptually to read and think about. Let's say it one more time. Combines each row in one table with every row in another table. Okay, so what does that mean in terms of the information? Here's an example. If you take classes here at Gateway, chances are you'll probably take more than one class. We'll have one table that lists all of our students. You're only going to be in that table once, right? I can't have two of you. I mean, then you're not really a unique entity, right? So you're in the student table once, but you're in the course table many times if you take many courses. So the one row in the student table would connect up with many rows in the course table, unless you only took one course in your life, right? So that's what they mean by that. Does that make more sense now? And I wish they would say it more clearly, but that's what they imply. So here it says select star from retail order item. All right, to me, by reading that one statement, it does not directly say what the top statement does. It doesn't at all. So is this implicit or explicit? Implicit, right? Or is it explicit?
Sounds like both.
It sounds like both, but there actually is an answer. But it says, this is mathematically known as the Cartesian product of the rows in the table. This is illogical in database work because we only need rows that somehow logically correspond in the two tables. So let me just run this. Will this run? I'm getting some nodding here in the room, so it must run, right? Because you've tried this? Right. It will actually run. Now, without having a complete breakdown of the table, is it doing what we think it's going to do? Well, we really kind of don't know. What I do see, though, is this, that I have order number, store number, blah, 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 and then I have order number again, and, okay, so what's the difference between the two? Well, they're different tables. We're seeing the output of both tables at the same time, right? Say that a little louder. Well, we will have some information that's duplicated, but for me it seems like these rows, this one, all the way up through order total, are all part of one table, and then it starts, the next table is listed here. Now how that information combined makes any sense, but it worked. We did join the information from two tables together. How exactly we did that, it's not entirely clear from just looking at the output. All right, so let's go to the next thing. It says, by selecting rows, by matching the primary key values of one table with the foreign key values of the second table, we can produce what we call a SQL inner join. And then what happens here, and this syntax becomes pretty important in my mind. So it says select star from those two tables, and now we're adding a where clause. And it says this table, retail order, dot order number. And order number happens to be the primary key of that table. So what is the primary key of the table? We haven't really talked about that quite yet. But I can go into the table, and let's see, here's our retail order, and you know what, I'm going to just look at the columns, and yes, there is a key here, like a key structure, so I can just go right to the key. But if you look at all the columns in the table, you notice how one's got this little icon of a key in it, and that is what we call a primary key, PK, and that is how we're basically ordering our table. So that value must be unique in that table to make that row unique. All right? So we're basically joining the order number here, right, equals the order number in this table. So let's look at the other table. Right? So notice order number, that's also a primary key there. However, notice this other designator here, FK, it's called a foreign key. Now we haven't really discussed this topic per se yet, But often when we do these joins, it is by virtue of the fact that we have a primary key or a foreign key relationship from table to table. And we'll see that as we go. So now we're explicitly saying that we're going to link from this table to this table using that field. Now we're getting more explicit with it. And it says, because the SQL join keyword does not appear, this is an implicit join. So when do you know it's explicit? So just be aware for like a test or something. Explicit means that the word join is there. That's all it means. But we're saying that this order number basically equals that order number, two different tables, but those two fields tie together. All right. Let's actually try to run that one. And actually, do we need to run it? Are we okay just looking at the output on the slide here? All right, let's just take it for what it is. And is the output different? It's kind of an interesting question, right? Because we did this join, and there's 21 results. Here there's only 7. What is the functional difference? I'm sorry, I can't hear you guys.
I'm sorry, what was the question?
What is the difference between the two outputs that we just saw? I mean, this is a much shorter list, and if you don't believe that it actually outputs a shorter amount of information, let's leave this query alone. Let's get a new one going and run it. Oh, it doesn't like it all of a sudden.
I don't think you want the database, that's what. You're not on the right database.
Oh, just strike 2. All right, now let's run it. All right, so it doesn't really output 7. So what is the difference between, the one and the other? And I'm kind of hovering here so it doesn't pin.
So you're putting like 24, those order numbers that equal in both tables instead of everything. So you're saying what, in the left table or in the first table?
It's a functionally different result though, isn't it?
It's multiplying, it's doing multiple records from the first table to match all the occurrences.
Bingo. Now, Brenda, can you say it really loud?
I don't know if I can say that yet.
No, you can say that again. Because you got it spot on correct. So it's taking multiple instances of the first table to narrow down output from the second table. Yeah. And they look at it as Cartesian multiplication. For whatever the heck that means, right? If we want to go study it from a mathematical principle. Here's what's really interesting about this stuff though, guys. The logic that we use to put databases together is based on a pretty new branch of mathematics in terms of the structure of the logic of it all. And that's coming up in a couple of slides. And we'll talk about that in a second. And I'm kind of like one of these, geeky people that, I used to hate math when I was a kid, and then when I studied it like properly, at the higher levels, and ran into teachers that knew how to teach it. That's kind of another thing too. Why do kids hate math? Because maybe their math teacher isn't that good. But then understanding like where the stuff comes from and why it was created, it becomes really fascinating to me scientifically. Because think about like even the Cartesian coordinate system. You guys know what that is? You guys ever have to graph an equation? Like you do an x and a y, and then you put in, for every value of x, like where does it plot? You might have curves or lines or whatever, right? So that it's based upon that, like when that kind of math was developed. This is really kind of interesting. Like 1600s. Maybe a little, and I'm guessing on the date, but it was around that time. It was really during the Renaissance that stuff started to come into play. And so a lot of the mathematics that people used for thousands of years is kind of lost and then relearned and then given formal names, and then the reason we have our whole scientific revolution now is because of all the new theories that have been developed based upon, things like calculus. That's a new branch of mathematics. Cartesian coordinate system, even though the Egyptians kind of had it figured out, they didn't name it that, right? If you think, if you really start to think about this stuff, but the one that follows that really is very important for the people in the data analytics program, and that's not all of you, but some of you are interested in that topic, is really based on one of the latest branches of mathematics called set theory. And when you get into higher level studies, you learn how very, very important that becomes. All right, so the next one, we're basically ramping it up, and we're just putting an order by on it just to sort it. That's the next one. I don't think I need to demonstrate that one. All right, let's go to the next slide. And I know we're getting about to the halfway point here, so I'm trying to find the logical stopping point. Okay, so maybe another couple slides and then we'll take a break. All right, so it says querying multiple tables with SQL joins. It says the process of using the SQL join operation to join two tables is called joining the two tables. Okay, thank you very much. Thank you for explaining. Thank you. I hope you guys read, like when you read stuff, I hope you read it critically like that, or rather than scratch your head and try to figure out what it means. When tables are joined using an equal to condition, as in the example above, did they do that above? Right? Oh yeah, sure. They do this, right? Equal to. The join is called an equijoin. Interesting. When people say join, 99% of the time they mean equijoin. And that is true. So, and frankly, I think of it exactly that way. So when I think of joining two tables together, I'm thinking of like, well, what field is in both tables, and I'm linking them together. That's what it is in my mind, all right? So multiple joins can be used to process 3 or even more tables. And that's kind of what they were showing you before. Remember that one slide where I showed you how the tables connected? And the more complex your database gets, and more importantly, the more normalized it is, the more necessary it is to join them together just for data efficiency. All right. All parts of the SQL select statement can be applied to table display results. Yep, that's true. Okay. Let's move on to the next one. So they're kind of ramping it up a little bit, and they're doing some additional stuff. So they're doing a bunch of columns. They're summing the extended price and outputting it as a separate column, pulling in from two tables, and they're linking together the SKU. So they have one table that just lists the products and designates the SKUs, and then a separate one where you're ordering and the SKU is linked. All right? Then we're grouping it by the buyer, the SKU data, and the description, and ordering by the revenue descending. So the biggest order goes first, and then we list down. So what's happening here is we're actually pulling data from two different tables and combining it into one to really create something a little bit more meaningful for us to look at, which shows us who bought what at what price and who bought the biggest ticket item. It's not an unusual type of query to do. All right, let's move on to the next slide. We're going to do a couple more slides here and then we'll do the break. I said that before, but see it says 9 of 10, 10 of 10. It seems like a good place to stop, right? All right. All right, so let's talk about what we call an inner join. So a little bit different. It says, selecting rows by matching the primary key values of one table with the foreign key values of the second table, we produce what we call an inner join. And that primary key to foreign key thing is where this comes into play. Just because you're joining stuff together doesn't mean you're ticking those boxes. I hope that makes sense. All right. So let's take a look at the statement. So we're pulling in all the columns from the retail order. Now notice the keyword join thrown in now. See that? So now we're joining the two tables. Is this implicit or explicit? explicit. We're explicitly saying join. And what are we joining them on? So you see like how we're ramping up the syntax here, and we're joining them on those two order numbers being linked together. And then we're going to order it first by the order number, then by the SKU from the order number table. It says because the join keyword does appear, this is an explicit join. I hope that makes sense to you. Cool with that? Like you have a choice, right? No, I'm not cool with it. I need it all changed. All right. A lot of verbiage here, but I think the content here is pretty important. All right, it says, the SQL joint keyword is placed between the table names in the from clause, so we already saw that, where it replaces the comma that previously separated them. The on keyword now leads into a SQL on clause, which includes a statement of matching key values that was previously in a SQL where clause. All right, I'm not sure if that resonates with you. And it's like no longer used as part of the join. We're not using the where anymore, which makes it easier to read the actual restrictions on the rows. And I think that's really kind of why they developed it, you know, is to make it easier to see that. And if you compare to what they're doing here, you know, where they say from two tables where these two things are equivalent. The difference now is we're joining the tables on what criteria on this criteria. So it's just really replacing the where statement. Functionally, it's kind of the same. It says the older implicit SQL syntax is considered an archaic older syntax, but it still works. So what are they telling you? They would rather have you use the newer syntax. That's what it's telling you. All the database engines will still let the old fly through. Just that, like they let caps or not lowercase run through too. All right.
So it allows you to define your field that you're joining on versus using the primary key.
That is correct. It does indicate which fields you're joining, and it doesn't necessarily mean that they must be primary and foreign key either. All right. So does that mean you can't use a where clause? No, you still can use a where clause, okay? So I don't want you to think that you're eliminating that. You see the difference? So you can still put criteria in with that tool, but now we're going to pull in all the columns. We're going to join these two tables together. We're joining them on this field, order number, and we're still putting a where clauses, so we're filtering, and then we're sorting. And then you come up with something like this. All right, let's take a 5-minute break, and we'll come back. So, all right, back from the break and continuing on. And I want to like do a little bit of a kind of a comparison here between the subqueries, you know, the query within a query, and compare it to a join. They both do address multiple tables, so both of them allow you to pull data in from two different sources. However, a subquery only pulls in the topmost query is really the one that's doing the work. The thing that's interesting about the join is you can pull in from a number of tables. Now you can do that with the subqueries too, but you're also pulling in the data from all the different sources simultaneously, so it's actually, you know, ultimately a lot more powerful. It's really kind of the point of it. Here's some interesting terminology, and for those of you that are new to programming, here's a really interesting keyword, this thing called recursion or recursive. And I always like to give a little example of this. So have you guys ever heard of an operating system, and you know, Unix hacker types will have like heard of this, right? Or you know, a GNU. Well, it's an animal, right? Right. Okay. So it's actually a thing. But there's also an operating system called GNU, and what it stands for is GNU is not Unix. It's Linux, right? So it's not Unix. But the G in GNU stands for GNU. See what that means? So it refers back to itself. That's what recursion is. So I think that's kind of an interesting thing to think about. Because while that like maybe logically might not make sense to you, like why on earth would you refer to yourself? It's kind of like talking about yourself in the third person, you know, in a sense. But and it says in computer programming languages, it's a block of code that calls itself. Now, I know a couple of you have had the Java 2 class, or maybe a couple of you are currently taking it right now. And I know at least 2 people in here have taken that class. And we had a little assignment where we would work on what they call the Fibonacci sequence. You guys remember that one? Where we write a piece of code, and because of the way the number sequence worked, the answer to it was a method that would call itself, and it would keep calling itself until it solves the thing. And that seems kind of weird, but sometimes that's a really efficient way to solve a problem, so you don't have to rewrite the code over and over again. In a database situation, a recursive relationship is a relationship between 2 columns in the same table. So it's not quite the same as a programming thing, but what's happening is we're using the same table to refer back to itself to look for other information. So let's take a look at what they mean by that. All right. It says in this thing, in this example, there's a recursive relationship. The supervisor column holds the value of the buyer name column as data and serves as a foreign key referencing buyer name. Well, that's a mouthful, right? As the associated primary key. So let's see if we can deconstruct that a little bit. So it says the supervisor column holds the value of the buyer name column. So that, you know, I think the visuals sometimes help. And serves as a foreign key by referencing the buyer name as the associated primary key. All right, maybe that doesn't resonate even if I say it twice, right? And if you were to like break apart this table, what it's really showing you is that that's pulling in information from the buyer column to make it work is really kind of the best way I can explain it. So for example, you have a buyer name and a supervisor, but interestingly, the supervisor is also the buyer, not in the same record here. And then you notice that Cindy Lowe is in 2 columns and Pete Hansen's in both columns. Isn't that kind of interesting? But it's referring back to itself, is what it's saying. All right. Maybe that won't resonate with you immediately. Okay, so that's a little confusing. All right, so it says the solution is to use what we call table aliases by using 2 versions of the same single table. All right, so let's take a look at what they're doing. I want you to notice here what they're doing in terms of they're putting a little bit of a prefix in front of there, and that's really kind of a way where we set up what we call a schema to kind of explain what the thing is. So what they're saying is we're going to pull from the one table the buyer name and output it as a supervisor name, and we're just going to go through and do that over and over again, well, twice. And then we have the second table, and then because we're using it now as 2 separate tables, but they're still linked together, logically, we're doing the same thing as the previous slide, but now we're separating it out and pointing back to each other. And then instead of tying it in as we did previously, you kind of get this thing. So we get this supervisor name that's an output column and supervisor position that's an output column. And that way we see that Cindy Lowe buyer 2 correlates to Cindy Lowe buyer 2 here. And that might not resonate with you right away. It's a little weird to describe, frankly. I think you'll get, as you try to work through examples that call for that, I think it'll probably make more sense for you. All right, let's talk about what another concept here called an outer join. And so we have 2 tables. One's a student table, one's a locker table. And notice that the students, so you have like a list of students, they have a primary key, let's say their ID number, and then another column that shows like which locker belongs to them, okay? Now the foreign key ties us over to this other table. So, but that foreign key here means this has to be a unique value. So in other words, a student can't have, for example, 2 lockers. The school won't allow for it, right? And here, we have a separate table that indicates all the lockers and the connection. In this table, that number is the primary key, meaning it's the main value. It must be unique. But it's also feeding the value over to this table. And this sort of connection is called what we call an outer join. All right, let's compare that to what they call an inner join, and you tell me the difference. Now there's a clue right there on the screen. It says only the rows where the locker foreign key and the locker primary key are shown. Note that some primary keys and values are not in the results. So in the previous table, we do have some students that apparently don't have a locker, right? So their locker number doesn't even appear here. So what's the point of having it connect them? So by doing the join, and we're using an inner join now, it eliminates the data that doesn't exist in both tables. Does that kind of make more sense? I'm hoping. All right. Now, throw a little complication into the mix here. They have actually 2 types of outer joins. So there's a left outer join and a right outer join. So you'll see these in sequence. So for the left one, it says all rows from student are shown, even when there's no matching field. So in other words, when we're doing a left outer join, now we're seeing the nulls. So with these, Adams and Buchanan, I don't know what their deal is, but they've decided not to have a locker. But because we're doing a left outer join, we're still seeing the information. Now, what's the functional use of that? You can say, well, at least I can see who doesn't have a locker, I guess is the one part of it. Or it doesn't really help me if I'm just looking for somebody's particular locker. The right outer join kind of flips it a little bit, and isn't this kind of an interesting approach? So it says all rows from locker are shown even when there's no matching, foreign key, primary key relationship. You see the difference between the two? How would you describe that difference? You could say on one the nulls are at the bottom, the other ones are at the top. Is that maybe where your head goes? But you see how the right outer join eliminates the person's names that don't have the locker? Now, this is the kind of thing where if you're strategic about how you structure it, you can use this information to narrow down search results. So that's really kind of the functional aspect of it. So let's take a look at the example that they have here, where they talk about the right outer join. All right. So take a look at, they're using the approach now where they're putting the stuff into separate tables with different prefixes. And so they're using order item, and what do you suppose that one stands for? SKU data, right? So they're coming up with clever ways to make them unique, basically. And then they say, from order item as right outer join. You actually say that as a keyword, and you also indicate that alternate table name for the same set of data. And when you choose names like that, you don't have to be quite so simplistic. You don't have to just say OI. You could actually make it much more verbose. And I think that's actually a modern convention now as people are starting to get more verbose with it. And then they're adding the on statement to do the link. So we're still linking off of SKUs. But we're linking back to which table? Both of them. That's really the answer there. And then you're ordering by a thing. Now notice the null values are included, right? And really what we're saying here is that if these are null, what does that indicate? There's no sales. That's what that indicates. Now that might be pertinent information. So whether or not you decide to do a right outer join or left outer join, it really kind of depends on what you're trying to drive the data to do. Some of that gets a little fuzzy when you start to think about these joins. And people actually thought about this stuff well before we had databases, which always blows my mind that there's these people that think so far ahead before we even have the technology to do what they're thinking about, right? And I was just mentioning, I think off video here, that one of the newest developments in mathematics has been this thing called mathematical set theory. In fact, I think it's only about 150 years old in conception, maybe a little older than that. But it says they use this term set theory to describe mathematical operations on a set, where a set is defined as a group of distinct items. Now, can you see how that ties into databases? So somebody was thinking about, if I take groups of students, so for example, if I say, here's my group of database students, and then Brenda, you're in my Java 2 class right now, then I have my group of Java 2 students, right? Two different sets of people, right? And if you think about it, the students are really unique entities, so if I was putting them in a database, they would each get their own row, and I could put in characteristics to describe each one of them. Now, Brenda, you would know that you belong to both sets, right? So I can use that to connect you together. So I can connect the two sets together because there's a common way to do it. Both of them contain students, and it just so happens that I have a student in common, right? And so somebody was thinking about these concepts, and it just blows my mind that they were thinking about this before we had the technology. I always, like to point that out. It says a relational database table meets the definition of a set, so it's little wonder that SQL includes a group of set operators to use for SQL queries. And it does not come from thin air, right? So whoever thought about this stuff, 100, 200 years ago, was pretty far ahead of their time. All right, so now this might jog your memory a little bit. It certainly jogs mine. Like when I was in school, and I think I might have learned this maybe as early as grade school, I think, like 5th grade or something weird like that. And then of course, as you go through school, they kind of repeat it. And then I got to the point where in my master's program, I studied what they call discrete math. You guys may have heard of that as a branch of mathematics. And discrete math is built entirely upon these constructs. But a lot of it is Venn diagrams. And Venn diagrams, and you'll see it on the next slide, are a way that you can apply a visual to the concept that we're talking about right now. So we're going to have a sets represented by a circle, a subset, a union, an intersection, and a complement. So and maybe you guys have learned this, and I want you to see that where some of these words come from. It says a union is equivalent to the logical or, and an intersection is a logical and then a complement is not A, not B. Okay, that one's always a mind blower for people, but seeing it in a picture really helps to explain it. All right, so think back to what I was just talking about. I have my database class, and I have my Java 2 class, okay, so A and B. Just so happens that they overlap. Okay, so I have one person in common for both, so that person would sit right here. They're in both circles, right? And so that union, when we say union, we're actually combining both circles together. So if I say the union of my database class and my Java 2 class, I would basically take all the people, all the unique people that are in both groups. Some people might be in both, but then I think of them as one collective. So when I think of every semester that I teach, I might have, let's say, 5 classes that I teach. And then if I think of the union of all 5 of those classes, I form one big group of students. Sometimes those students are in multiple classes and sometimes not. It just kind of depends. If I wanted to just figure out the intersection, right, then I look at just the person that's in common and exclude the rest. So in this case, Brenda, it would be you, right? That would be you right there, the little purple area. All right. Let's go back up to the top then and say that a subset, now let's just hypothetically say you were the only person in that Java 2 class. Oh, it's close, but not quite. Well, in the face-to-face, we have a pretty big group actually online. So if everybody that was in the Java 2 class was also in the database class, then you would be in this circle. So then B becomes what we call a subset of A. All right, and I love the visuals on this because it really explains some pretty complex logical concepts with pictures, and when you see it in pictures, all of a sudden it's not really so complex, you know, because you can see what you're describing. Now the complement is a little bit different. So this one says the complement is the area in A that is not in B. So in this case, it would be like this database class with Brenda removed. That would be the complement. And then if you go back and look at the description of that, the not A, not B, do you see how like that's like really hard to read through? But then you see a picture of it and you're like, oh yeah, I see it. Yeah, no big deal, right? But putting a verbal description on it becomes kind of fascinating. All right. So how does this apply to SQL? So like once again we said, because SQL deals with collections of information, it is logical that on occasion you're going to have information that's in 2 sets or areas of information, or in this case tables, or for that matter databases. So some of the terms that we're using there do apply inside of SQL. So you can use the union, the intersection, and then the except in order to address those things. So let's look at an example. So with this example, okay, we're pulling in some columns from one table. And then we're looking for the union. So it's like we're running a whole separate query. So we're pulling in SKU description, and department from this table. And then we're doing SKU description and department from this table. So you can see that one's a 2017 catalog and one's a 2018 catalog. And if I join those 2 together, what that means is I'm going to take, now this is where I think the diagram is really helpful conceptually. What that means is I'm going to take both of the catalogs. There's going to be some items that were in both, but some items that might be unique, and combining them together into one result. That's the union. Okay? And I think that's a nice simple example. And once again, the graphic is worth its weight in gold. All right? We can also do the union all. And what's fascinating about this is this. The previous version, if something appears in both, it would list both. So if I was selling a tent 123 in 2017 and a tent 123 in 2018, it would list it twice. Yeah, see the problem with that? So what they've come up with is this. And I actually said that backwards, and I apologize. The union all would show the duplicate row, so I apologize for saying that. So the first one doesn't show the duplicates, this would show the duplicates. Why would that be helpful? I don't know. Functionally, I can't see the reason for it right now, but you might have a situation where it might actually be helpful. If you wanted to do an intersect, so just the stuff that appears in both is what that would be. Once again, go back to the diagram. So you would use the intersect command. You're running 2 separate queries. We want to see the products that appear in both versions. If we run the except, so what does this one do? And and this is kind of interesting too here. Notice MySQL does not support this operation, and Oracle database has a special minus operator for doing it. But the except, right, the result is all the row values in the first table but not the second. So which one does it correspond to? Well, the bottom one. Right. Yeah, and that one gets a little fuzzy because the description itself is kind of fuzzy. So we got union, union all, intersect, and except. All right, and that wraps up this part of the PowerPoint here. So I'm going to stop the recording, and then we'll move on.